Hello friends, welcome here to another episode of our online tutorial on Prep Station. And in this episode, we'll be looking at the topic simple harmonic motion, SHM. What is simple harmonic motion? Simple harmonic motion is the motion of an object whose acceleration is always directed towards a fixed point. The motion of an object whose acceleration is always directed towards a fixed point. And that fixed point is usually the center of motion. The motion is always proportional to the distance from that fixed point. Now, it is also the to and fro movement of a body from a fixed point. To and fro movement of a body or of an object from a fixed point. There are 2 points to note in simple harmonic motion. Number one is the acceleration, which is always directed towards a fixed point, which is usually the center of motion. And then the acceleration is directly proportional to the distance from that point. So these are the 2 basic points that you needed to know in simple harmonic motion. Now, let's look at the terms that come out frequently in simple harmonic motion. One of the terms is known as amplitude. The amplitude of simple harmonic motion is the maximum displacement of a body from its central or equilibrium position. The maximum displacement from its central or equilibrium position. Once a body is displaced from its equilibrium position, the maximum displacement from that position is what is known as the amplitude. Now, what is the period of a simple harmonic motion? It's a time taken to complete one oscillation or one cycle or one vibration, as in the case of a helical spin. So the time taken to complete one oscillation, one vibration, or one cycle is known as the period of simple harmonic motion, and the period is usually measured in seconds. Now, what is the frequency of simple harmonic motion? Is the number of oscillations that can be completed in a second. The number of oscillations that can be completed in the second, and is usually measured in hertz. Now, let's look at a few formulas that we have in simple harmonic motion. We have what you call your angular velocity. And your angular velocity is usually the rate of change of displacement with time. The rate of change of displacement with time, which can also be given as 2 pi f. We also have v, which is your linear velocity, which is your angular velocity multiplied by your amplitude. Then we have t, which is the period of motion, is given as 2 pi all over your angular velocity. And you have your linear acceleration also, which can be given as angular velocity squared multiplied by your amplitude. Now, looking at a diagram of simple harmonic motion exemplified here, we can see that a body or a ball moves from point A through its equilibrium position at O and then moves back to B. Point A and B are their maximum displacements from their equilibrium position. So they have their maximum amplitudes at point A and B, while point O is the equilibrium position. So you can see the diagram. So everything is properly exemplified here, as we can see. So let's look at the energy transformation that happens in a simple harmonic motion. Now, if you see from the diagram that has been displayed on the board, you can see that there's a bulb has been displaced from its equilibrium position, and the positions are at position R and position Q, and then it passes through position C, which is its equilibrium position. Now, at the 2 extreme positions, which are position P and Q, you have your maximum potential energies at those points, while at the equilibrium position, you have its maximum potential energy. Now, in simple harmonic motion, the restoring force that tends to bring the body to equilibrium shows the fact that energy is involved, because there's always a restoring force. So at any point in motion, there is either kinetic energy, potential energy, or the both. So this leads us to the fact that energy is conserved during a simple harmonic motion, and that energy that is conserved is always constant. Now, at the 2 extremes, you have the maximum potential energy, while at the middle, which is at the center of motion, you have your maximum kinetic energy. Now, if we go back to conservation of energy, at any instance of motion, the simple pendulum has a total energy in the system, which will be the kinetic energy will be equal to the potential energy or the both of them. So if you look at the total energy in a system, kinetic energy is given as half mv squared, while potential energy is given as mgh. Now, it's either the potential energy will be equal to the kinetic energy or equal to the both of them. So if we want to look at the maximum velocity during motion, we can equate our kinetic energy to our potential energy. And once we do that, you're going to have half mv squared is equal to mgh. Now, m is common to both potential energy and kinetic energy, so they cancel out. While v squared now will give us square root of 2gh. That gives us the speed of motion at any instance during simple harmonic motion. Now, let us look at a few questions under simple harmonic motion here. Now, what is the frequency of vibration if the balance wheel of a wristwatch makes a revolution of 90 revolutions in 25 seconds? The first option there says 0.1 hertz, B says 0.04 hertz, C says 2.27 hertz, while D says 3.60 hertz. Now, we know that frequency is going to be the number of revolutions divided by the time taken. If you notice here, they told us that we have 90 revolutions in 25 seconds. So the frequency of vibration here is going to be 90 divided by 25, which will give us 3.6 hertz. And so if you look at the question carefully, the right option there is option D, which is 3.6 hertz. Now, let's look at energy that is stored in a loaded spiral spring. Like I said earlier, a loaded spiral spring is also an example of simple harmonic motion. The maximum energy in a string, which also is known as work done, can be given as half a k a squared. K is usually the spring constant, while a is the amplitude of motion. Now, at any point during the oscillation of the spring, we will have kinetic energy equal to potential energy, which is also equal to the maximum energy at any point. So the total energy there is going to be your potential energy and your kinetic energy. Now, if we go forward, we look at the question here, which says the length of a displaced pendulum bulb that passes through its lowest point twice every second. So calculate the length of a displaced pendulum ball which passes through its lowest point twice every second. The first option says the length is 0.2 meters, 25 meters. Second option says B, 0.45 meters, C, 0.58 meters, D, 1.00 meters. Now, if you look at this question carefully, we are told that the ball passes through its lowest point. That means it makes one complete oscillation. That means it makes one complete oscillation. That means the period of the oscillation is equals to 1. So now, if you look at the formula, T is equals to 2 pi square root of L over G. Now, if our T, which is the period of motion, is 1, and then we substitute into the formula, G is given as 10 meters. With the right substitution, you will notice that our value for L is going to be 1 all over 2 pi squared multiplied by 10, which is gravity. And your correct answer there is going to be 0.25 meters for that question. Now, let us look at the energy in a loaded spring. The period of motion is for a loaded spring is given as T is equal to square root of 2 pi all over omega or 2 pi all over square root of m over k. The period depends on the mass and the force constant and not the amplitude of motion. So for a loaded spiral spring, the period does not depend on the length. Okay, so let's have another question. Question says calculate the period of vibration of a spring system of force constant 200 newtons per meter when the loaded mass is 2 kilograms. The options there are 0.53 seconds, B 0.63 seconds, C 0.33 seconds, D 0.23 seconds. From here, we are giving the first contact 200 Newton per meter, and then the mass is given as 2 kilograms. So if you look at the period for a loaded spiral spring, the formula is given as 2 pi square root of m all over k. So if we substitute the value of k and m into this equation, we are going to have the period of vibration, which is 2 pi into square root of all over 200. So with the right substitution, you are going to know our answer here is 0.63 seconds. And from the question, we can see correct option is B, which is 0.36 seconds. Thank you. Friends, we will come back. Let's have a break.